Hi everybody, we're going to pick back up with chemical bond formation. If you're following me in the course pack, this is pages 9 through 13. So I'm going to review something we covered in a previous PowerPoint, the one that's titled Basic Chemistry and Introduction. In that PowerPoint, we talked about reactive atoms versus stable atoms. So you may recall that atoms that are stable satisfy either a duet rule, which means that they have at least two atoms or electrons filling that innermost orbital of the atom, or they have 8, which satisfies an octet rule in the valence shell. So if you take a look at these two atoms here, let's talk about the one on the left first. The one on the left has, let's see, looks like 8 electrons in that valence shell. And so that means that it satisfies the rule called the octet rule. Okay, and since it satisfies the octet rule, we would say that this is a stable atom. It has no interest in forming a chemical bond to either gain or lose electrons. Now, the atom on the right is a different story. We're not looking at the innermost orbital. That's not the one that's of interest here. Always look at this valence shell. Okay, that valence shell is going to tell us a story. In the valence shell, we're looking for 8 electrons, which would satisfy the octet rule. That's what would create a stable atom. But this one only has, looks like 4 electrons in that outermost orbital, or valence shell. Therefore, we would say this particular atom here is reactive. Okay, so this atom on the right is the one that's going to be participating in some type of chemical bond formation, whether it's a share or a transfer. We'll talk more about that in just a moment. So there's 2 types of bonds that we're going to discuss, ionic bonds and covalent bonds. There is a third type of bond called hydrogen bonding that's a little different from the way these two are set up. So let's talk about the word ionic to begin with. You can see the word ion hidden in here, and ions are no longer neutral atoms. These are atoms that have either lost or gained electrons in order to create a stable valence shell. So to have a stable valence shell, we're looking for either the duet rule being satisfied or the octet rule being satisfied. So on the left here, you'll notice that we have this particular atom with only 1 electron in its valence shell. The atom on the right has a total of 7 electrons in its valence shell. Neither one of these right now are stable. Why is that? Well, neither one satisfies the octet rule. Again, let me remind you, don't look at the innermost orbitals, okay? Look at these valence shells. These are the outermost orbitals. They're the ones that we're going to examine to see if they have met that octet rule. So this particular set of atoms is going to transfer an electron from the outermost orbital of one atom to the valence shell of the neighboring atom. In doing so, you'll see here in the after picture, we have lost that valence shell on the atom on the left, and we've created a stable valence shell here, which satisfies that duet rule. By transferring this electron here on the right, we've now also created a stable valence shell and have now satisfied that octet rule. So we've got 2 stable atoms here. Both of them have satisfied their rules, and they have stable valence shells. Now, if you pretend that you've never seen the picture on the left and I've only shown you the picture on the right, you might say, well, how do I know there's been a transfer of an electron that's taken place? Well, just count the charges. Neutral atoms should have the same numbers of protons and electrons, but here we have an unequal amount. This atom on the left has only 2 electrons. That means we have an overall 1 charge, positive 1 charge. On the atom on the right, we have 9 protons in the center there, the nucleus, and now we've got 10 total electrons. That means we have an extra negative charge. These are no longer neutral atoms. These are now called ions. In fact, the negative ion is called an anion. Hey, there's a great prefix, right? An means negative. And cations are the ones that carry a positive charge. So if you remember that cat has a T in there, kind of looks like a plus symbol, that's a great way to remember that cations carry a positive charge. A student years ago once told me this old saying, it's better to give than receive. Well, the ones that give away an electron carry a positive charge, the atom that receives an electron has a negative charge. So the name of the game here is all about the transfer of electrons in order to create a stable valence shell. Now in this picture, I'm showing you only the transfer that has taken place. I'm not showing you the before picture. So you want to be able to confirm that there's been a transfer of an electron or more taking place here. So on the atom on the left, we're just going to count the charges. There are 11 positive protons. And then I'm going to count the electrons. There's 2 in the innermost orbital and 8 in the valence shell, for a total of 10 electrons. Doing the math, that means I have an overall extra positive charge. Now, the atom on the right looks like it has 9 positive protons. It also has 10 negative electrons, giving us an overall negative charge. Okay, so that one's going to be our anion on the right and our cation here on the left. Okay, so that means that the transfer took place from which direction? Did the atom on the left give to the one on the right, or vice versa? Well, the atom on the left must have transferred an electron to the atom on the right. Remember that atoms or electrons rather carry negative charges, and that negative extra electron comes to reside on this valence shell of this atom on the right. Okay, so are these two atoms now stable? Yep, they're stable, but they're no longer neutral because now we have had a transfer of at least one electron. Okay, so let's switch gears now and talk about covalent bond formation. Hey, before you go any further, take a look at this word covalent. Co and valent. Okay, just split it right there. Co means together. And do you see the word valence? So there's a great clue built into this one. This type of bond results when electrons are shared between atoms because their valence shells are together. So take a look at the picture down below. You have 2 atoms. Each one has only a single electron in the valence shell. It wouldn't work very well to transfer an electron between these valence shells, would it? One would be a winner and one would be a loser. So let's take a look at what happens as a result. On the picture on the right, you'll notice that the electrons are shared now between those 2 atoms. The sharing process allows for each atom to have a valence shell that is now stable. So we have now satisfied that duet rule. You'll notice that these 2 electrons are sitting kind of over both valence shells simultaneously. That allows for them to travel around one orbit and around the other orbit at about the speed of light. You know, I know that these atoms are not living beings, but if you were to imagine that they were, they wouldn't know the difference. They wouldn't realize that half the time the electrons are spending time around the neighboring orbital. So it satisfies the duet rule because we're sharing this pair of electrons. Let me draw your attention here. While ionic bonds transfer electrons, covalent bonds are results of sharing pairs of electrons, always in a pair. Okay, so keep in mind, it's like buying shoes. If you've got 2 feet, you're not going to buy just a single shoe. You're going to go buy a pair of shoes. Covalent bond formation results from sharing in pairs. Okay, so there's 2 types of covalent bonds we really want to talk about here. Non-polar covalent bonds, which is what you're looking at here, and we'll talk in just a moment about covalent bonds that are polar in nature. In this picture, you'll notice it looks like a tug-of-war is taking place. In non-polar covalent bonds, there's an equal share of electrons, and so there is no one getting any more time with the electrons than the other atom. So it's an equal share of electrons. Okay, non-polar means an equal share of electrons. Polar covalent bonds, however, result from an unequal share. And if you imagine kids on the playground, there's always some kid who wants the toys, right? Somebody who wants to play with them more than anyone else and will hog the toys. That's what happens with polar covalent molecules. You have an atom in the molecule that really, really wants those electrons, so it pulls more strongly on those electrons away from the other atoms. If you've had chemistry before, you probably have heard of the term electronegativity. In this picture, you're looking at a water molecule. Water is H2O. This is a hydrogen atom here. Here's another hydrogen atom, and here's an oxygen atom. So you'll notice the electrons here are being pulled toward the oxygen atom away from those hydrogen atoms. That creates what we think looks like a Mickey Mouse set of ears. Kind of like this, right? Okay, so these electrons here and here are being shared between the oxygen and the hydrogen atom. So in other words, you have an oxygen atom here sharing a pair of electrons with a hydrogen atom, and another hydrogen atom sharing a pair of electrons. So in reality, that's the picture that you're looking at here. Keep in mind, polar covalent molecules result from a sharing of a pair of electrons, but it's an unequal sharing. Since the oxygen atom tends to be the greedy atom here, it pulls more negative charge electrons toward it. To represent that it is the more greedy of the atoms, we place that delta negative symbol here by the oxygen atom. That little symbol is a lowercase Greek delta, delta meaning a D, and so the negative implies that we're getting more of a negative charge. The delta positive symbols that you see here represent that those two atoms carry more of a positive charge, not a full positive charge, but a slight positive charge. Anytime you see these little delta symbols, positive and negative, you're to assume that you're looking at a polar covalent molecule. That represents an unequal sharing of electrons among the atoms in that particular bond. So water is a great example of a polar covalent molecule. It makes up around 65% of your body's mass, and it plays a major role in influencing how things behave in your body, since it is a polar covalent molecule. Just another view of water here. Notice these are our great clues to look for. These delta positives and negatives mean there's an unequal sharing of electrons that are taking place. So here you can see a tug of war that's not quite fair. This is hydrogen and chlorine, it looks like, and we've got a tug of war that's going more toward the chlorine than toward the hydrogen. So in this case, if the electrons are coming more toward the chlorine, I put a delta negative over there, and if hydrogen's losing out on this battle, I put a delta positive on that side. This is shorthand. This is a way for us to notate bonds and how many electrons are shared in those types of bonds. Single covalent, double covalent, and triple covalent can be represented by lines. A single covalent bond can be represented by a single line between two atoms. A double covalent bond can be represented by two lines, not to be confused with an equal sign. So if we have two oxygen atoms, we might say there's a double bond there and simply represent it by those double lines. Guess what? Triple bonds have three lines. These two nitrogens may be held together by three lines. That represents a triple bond. So that's a single bond, a double bond, and a triple bond. Okay, so don't confuse the bond with the number of atoms. The number of atoms here can be represented by the subscript down below. So that's still two hydrogens, that's still only two oxygens, and that's still only two nitrogens. But the way they bond together is a little different. So in this image, you can see the picture on the left shows us the pairs of electrons being shared between each carbon and hydrogen in this bond. Okay, I'll circle those. Now, you'll notice on the right, there's a single line there that allows us to understand that there's a pair of electrons shared between each hydrogen and the carbon, which is the central atom. In this picture, we can see 4 total electrons being shared. Those 4 electrons means that there are 2 pairs of electrons being shared. This is quite a mess to draw, so every time we want to talk about it, we can simply use this double line here to indicate a pair of electrons being shared. So 2 lines is a double bond, 2 total pairs of electrons being shared. 3 nitrogens here are held together by 6 total electrons. You can see them right there. And there's quite a lot going on. That's a very strong bond because you've got so many electrons being shared in the pair. This time we use 3 lines to represent these pairs of electrons. Keep in mind, 3 lines, triple bond, 3 pairs of electrons are shared. So in summary, you can use this kind of picture if you want to illustrate how the electrons are scattered throughout the valence shells, or you can simply use shorthand. Keep in mind, all of these are covalent in nature. Okay, there are no ionic bonds in this picture. You have single bonds here on the left. You have single and a double bond here between the two carbons. And you have single bonds and a triple bond here between these two carbons. So let's talk a moment about what you see in this picture. You may recognize the delta symbols. The delta symbols tell us we have a polar molecule. These are in fact water molecules. Here's your oxygen and your hydrogens. Okay, another water molecule over here. There's our large oxygen and smaller hydrogens. And you may notice there's a dotted line here connecting between these two atoms. Now, these are two different molecules that have an attraction to each other. You'll notice this hydrogen carries a slight positive, represented by the delta positive symbol, and you'll see over here a delta negative on the oxygen atom. Okay, so this is kind of like a slight attraction. It's not a really strong attraction, but it is what is keeping these water molecules attracted to each other. We call it hydrogen bonding because oxygen is attracted to the slightly positive charge on the neighboring hydrogen atom of that molecule. Okay, so if there was another water molecule over here, there might in fact be another delta charge between the, well, it would be that way, wouldn't it? Between the hydrogens and the oxygen. Okay, so the clue word here is look for these dotted lines. Those dotted lines represent for us hydrogen bonds. Here's just another view of those dotted lines between neighboring water molecules. Hydrogen bonding is what allows water molecules to stick together and be cohesive. This plays a major role in when we discuss how water behaves in the body, something we'll do a little later on. Just a quick self-test here on some chemical bonds. All right, the type of chemical bond that you see here is ionic. The way I know that is because I see a positive charge here representing the cation and a negative charge here representing the anion. So also the covalents, the two outermost orbitals, do not touch or overlap here. So that helps me to eliminate that this is not a covalent bond, it is an ionic bond. All right, so here we have carbon with 4 hydrogen atoms. The type of bond here is covalent. Each bond between the carbon and the hydrogen is single, okay? And there are no delta symbols, so this one is nonpolar. So a lot we can tell from this picture. It's covalent, the bonds are single covalent bonds, and there are nonpolar setups here because we have an equal amount of sharing. Everything here is a single covalent bond, except for the double bond here between the carbon and the oxygen. All right, look closely. There are 4 total electrons being shared here between these two oxygen atoms. And because there are 4 total electrons, this must be a double covalent bond. So you say, wait a minute, 4 gives me a double? Yeah, it's because 2 electrons are in a pair, and we're sharing 2 pairs of electrons. So this is a double covalent bond. You know it's covalent because these orbitals here, they tend to overlap. Covalent, meaning together with the valence shells. All of these are single, covalent, and nonpolar in nature. I see orbitals overlapping. I see a pair of electrons being shared between the carbon and each fluorine atom, and I don't see any delta symbols. That reminds me that this is not a polar molecule, it is a nonpolar molecule in which all of the sharing here is done equally. Hey, great clue, dotted line. What type of bond is this? It's a hydrogen bond. Okay, and this one here has a double covalent bond between the 2 carbon atoms, represented by a pair of lines here. And these, of course, are single covalent bonds here. No delta symbols means nonpolar covalent molecule. Finally, here we have a lithium ion with a plus charge right there, and a fluorine with a negative charge. Notice these 2 atoms are sitting nearby, but their orbitals do not overlap. Therefore, we conclude this one is an ionic bond, and there's been a transfer of an electron between these 2 atoms. In fact, lithium gave an ion, or an electron rather, to fluorine, causing it to become an anion. So how did you know that? Well, the negative charge means that there has been a gain of electrons. The positive charge means there's been a loss of electrons. Just a little bit about some rules here with looking at molecules and compounds. This information is also in your course pack. Instead of reading this to you, I'm going to work you through a few problems. A single hydrogen atom would be represented by its symbol, which is an H. There is no need for a 1 to be placed anywhere. A single H means an atom. And of course, the 1 is an understood number. These are two hydrogen atoms. Here, of course, and here. And they're not bonded together. Okay? So there's a couple of options. I want to tell the person I'm talking to that I have two single separate hydrogen atoms that are not bonded. Therefore, I would pick this one here. 2H implies that I have two hydrogens, not bonded together. Had I selected H with a subscript of 2 down there, that would have implied that those two hydrogens would have in fact been bonded together. So we pick the one with the coefficient in front. That 2 in front is called the coefficient, and it allows me to know that I've got two separate unbonded hydrogen atoms. Here, of course, is a set of hydrogens bonded together. We could do it this way, or we could do it this way, H with a subscript of 2. So when you see the subscript, that implies to the person looking at it that there has been a bond formed between those two hydrogen atoms. All right, a little more complicated here. I have 4 total hydrogen atoms. I have 2 paired together here, and I have 2 paired together here. So I've got a lot of options. It looks like a pretty good list, right? So which one do you think is the best way to represent what we're dealing with here? Well, we won't pick the first one because that tells me there's 4 separate hydrogens that are unbonded. In fact, 2 of them are bonded to each other. H4 implies that all 4 hydrogens are bonded together. That's not the case. 2 are bonded in one pair and 2 are bonded in another pair, so we're going to remove that one from the list. The third option gives us the best choice. H2 with a subscript implies that we're dealing with a pair of hydrogens bonded together. And because there's 2 molecules, we'll use a coefficient in front to indicate that we actually have a total of 4 hydrogen atoms. So when you have something like 2H2, you multiply the 2 times the 2 to get a total of 4 atoms. So yeah, there's actually 4 in this molecule or in this, this chemical formula, but what we want to illustrate to somebody is that we've actually got them separated. All right, so I'll just work you through these practice problems here for just a moment. For number 1, the type of bond shown between those carbon and oxygen atoms are double bonds. For number 2, an atom with an atomic number of 7 and mass of 15 will have 8 neutrons. That's because 15 minus 7, of course, is 8. The type of bond that results from the unequal sharing of electrons, well, unequal means polar. Sharing means covalent. So this is a polar covalent molecule. Number 4, how many atoms of sodium are in this compound? Well, sodium is Na, not S, and so there are 2 atoms in that compound. We know that by the subscript. For number 5, how many potassium atoms are in this compound? Keep in mind potassium is K, not P. P is phosphorus. The subscript of 2 tells us that that's how many atoms we have. So number 6 says how many electrons are in the valence shell of nitrogen with an atomic number of 7. You must know that the atomic number of 7 equals the number of protons, and that equals the number of electrons. So that means there are 7 total electrons. How many should we place in the innermost orbital? Well, it only holds 2. And when we draw another orbital, we actually have room for the remaining 5. Okay, so there are 5 electrons in nitrogen's valence shell. And by the way, it's reactive, not stable. For number 7, What is the mass number of sodium with 11 electrons, 12 neutrons, and 11 protons? Well, I need to add some stuff together. So what do I add? I add the numbers of protons and the number of neutrons. So I should have a mass number of 23. For number 8, the types of bonds present here, these are all double covalent bonds. And finally, the last one, isotopes vary from one another by the number of neutrons in their nucleus. Okay, they have the same numbers of protons, they are the same elements, same atoms of the same element, but they have differing numbers of neutrons.